So what we're going to do today is we're going to do a quick review of some of the topics we talked about in grade 10 science in terms of properties of acids and bases. But more importantly, what we're going to do is look at the theory. Now these theories are important, especially for grade 12 chemistry next year, because we're going to operate on them and use them to interpret a lot of different things. Okay, now, first off, you may or may not remember this chart for the properties of acids and bases. You can pause the video to copy it down. I won't read it all, but we know some of these things, right? From when we did our reactions with acids, we know that some metals will displace a hydrogen from an acid to produce a hydrogen gas in a single displacement reaction. We know from our reactions unit, double displacement reaction, some acids will react with a carbonate. We've talked about litmus, right? We've talked about how both an acid and a base form electrolytes and conduct electricity. Okay. Now, what's our theory of an acid and a base? Well, last year you worked on what was called the Arrhenius definition, and it was the early Arrhenius definition, where an acid was anything that, when added to water, ionized to produce a proton. Now, ionized is a key word here because it starts out as an entity with covalent bonds. The hydrogen that's released as an ion, for example from HCl, is covalently bonded to that chlorine. So they're not ions. But in the process of that hydrogen being released, the hydrogen ion, it forms an ion. And so that's why we call it ionization. And last year you probably learned that bases are ionic compounds when added to water that dissociate to release a hydroxide ion. Remember, dissociate is what happens to ionic compounds when they're added to water. Okay? Now, these theories, and also acids and bases react in a double displacement reaction and produce salt and water. This is fine. These theories are fine, except they don't cover all of the things that act as an acid or a base. And it doesn't explain, for example, basic properties of a number of different things. First of all, a lot of polyatomic ions act as a base. Okay? Or the fact that when I add my metal oxides to water, they also result in basic solutions and act as bases. Now we know from our reactions unit, a metal oxide plus water forms a metal hydroxide. And also the fact that it doesn't explain ammonia. Okay, so these things, this does not explain in these basic properties, or these compounds' basic properties. Also, it doesn't explain the acidic properties of some entities as well. Some things act as an acid that don't necessarily have a proton. For example, when I add non-metal oxides to water. Well, we know non-metal oxides react with water to form an acid, but also some metal ions. So for example, if I added aluminum chloride to water and I stirred it, it would have acidic properties. So it would cause, for example, the pH to go down. Okay? Remember, pH is a measure of the amount of protons or hydronium ions in the water. Okay, so as a result, we needed a new theory. Well, to do this new theory, what we need to do is we need to first understand what we talk about when we talk about a hydrogen ion. When we talk about a hydrogen ion, this is a hydrogen that's lost its one electron, leaving it with only a proton. That means that it's a very strong positive charge because it's condensed into a tiny area, and so as a result, it'll be attracted to negative charges. And when we're in water, the thing with the most negative charges is the slightly negative end of the polar water molecule. And so as a result, what happens is that any protons that are released, or hydrogen ions released into water, will quickly grab onto a water molecule and form what's called a hydronium ion. And so with a hydronium ion, I have 3 hydrogens bonded to an oxygen. It has a charge of +1. Okay? Now, hydronium is the way that my hydrogen ion or proton is in water. But just so we know, chemists are often lazy, and we often just write it as an H plus aqueous. But this is how it really exists in water. Okay, now, so as a result, we revised our Arrhenius theory. And we said for our earlier Arrhenius theory, well, it's just things reacting with water to either form a hydronium ion or a hydroxide. And so, for example, when I add my HCl to water, it reacts with the water to form my hydronium ion and a chloride ion. Or when I add some of my bases to water, for example, my ammonia, it will react with water to form ammonium ion and a hydroxide ion. Or with my carbonate, it will react with water to form a bicarbonate and a hydroxide. And so this helped us explain the basic properties and acidic properties of a number of different things, but it didn't explain everything. And so as a result, we need to continue to expand our ideas. And it didn't explain some of the reactions. So we have a new theory, and the theory that we work on now is called the Bronsted-Lowry theory. And with the Bronsted-Lowry theory, it treats acids and bases in terms of how they respond to the proton. How do they respond to the H+? In terms of, do they accept an H+, or do they donate an H+? And that's what defines our acids or bases. And so in our Bronsted-Lowry theory, we define an acid as a substance that donates a proton. And we describe a base as a substance that accepts a proton. And so when we look at our acid-base reactions, it's just a proton transfer. So if we take a look at our HCl when we add it to water, the HCl is my proton donor. I know it's a proton donor because it starts with a hydrogen or has hydrogen up at the front. My water can accept a proton to become H3O+. The chloride ion is what's left behind. Okay, so I have my proton donor, or my proton acceptor, and I form that. Okay, now I form my hydronium ion. My number of hydrogens goes up on my proton acceptor, and the charge goes up by +1. Now my proton donor, proton acceptor, don't have to be water or hydrogen acid. But I can have a proton. So here water was a proton acceptor. In this case, it's going to be my proton donor, because my ammonia can accept and the water can donate. And so when the water donates, it's left with an OH minus because it gave up an H plus. And with my ammonia accepts, it becomes ammonium and has one more hydrogen and an increased charge of +1. So in this case, water was both a proton acceptor and a proton donor. So this refers to, and a lot of substances can both donate and accept protons. Another example would be my bicarbonate ion, HCO3 minus. It has a -1 charge, which means it can still accept an H plus, but it also has acidic hydrogen that it could give off. Okay, and so we call these things amphoteric species. They can be both a proton acceptor and a proton donor. Now I want to point out that to be a proton acceptor or proton donor, my substance doesn't have to be water, right? So I could have HCl react with my bicarbonate, HCO3, and I'd form Cl minus and H2CO3. And then I could have my NH3 react with my bicarbonate, H3CO3 minus, form NH4 and CO3 2 minus. So my proton water does not have to be involved. Substances that can both donate and accept are called amphoteric species. Okay? Now, because of our definition of a proton donor, proton acceptor, we actually end up with, when I have my reaction between an acid and a base, having two acids or two proton donors and two bases or two proton acceptors. So we have a way of distinguishing. So when I look at my reactants, I have an acid here, and I know it's an acid because it starts with a hydrogen, which tells me that it's an acidic proton, which can be donated. Okay, so that would be my proton donor. And then I have my water. It can be both a proton donor and acceptor. So in this case, it's going to accept, and so it's going to be my base. When my proton donor gives up a hydrogen, it forms an ion because it has an ionized. Okay, and so now I have an ion here with a -1 charge. Since it has a -1 charge, it can pick up an H+. And also, conversely, I have a hydronium ion, which is a water molecule with an extra proton that I could release or donate. So as a result, I have both a proton acceptor and a proton donor here. So to distinguish between the proton donor in a reactant and the proton donor in the product, we call this a conjugate acid. And to distinguish between my proton acceptor in my products and my proton acceptor in my reactants, we call this a conjugate base. Okay? So my acid is my proton donor in my reactants. My conjugate acid is the proton donor that is formed. And my base is my proton acceptor. And my conjugate base is my proton acceptor that's formed. Okay? Now, we will often call this an acid-base conjugate pair because this acid formed that conjugate base. And this is a base conjugate acid pair because this base formed that conjugate acid.